and welcome back to Calculus 2. We are starting chapter 8, chapter on sequences and series. So the first two sections, 8.1 and 8.2, address sequences, and then the rest is about series. Then chapter 9 is power series. And then you get to use that later in your electrical engineering and your differential equations and so on. So we start with the definition, which says sequence is an ordered list of numbers. And I'm going to say AN as a sequence is equal to term A0, A1, A2, A3, A4, dot, 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 AN, dot, dot, dot. Ordering is done through natural numbers n. Ordering depends on set of natural, I'll put in parentheses, counting numbers n, which is the element of set n. Now that set element belongs to, which means 0, 1, 2, 3, 4. 0 is not really a counting number because you will not going to count 0 trees, 1 tree, 2 trees, 3 trees, right? But we do use it here, so we include it. Sequences can have finite number of elements, of numbers, or infinite. When I say elements, meaning elements of the set, which are the numbers in this case. And they're called, obviously, finite or infinite sequences. So let's see some examples. So I can use the formula to generate a sequence. Say AN is equal to n squared plus 1. Now we know that n is going to start 0, 1, 2, 3, 4, 5. Therefore the sequence is 1, 2, 5, 10, 17, 26, going on forever. This is the infinite sequence. You have the formula which generates the sequence. And it's easy to compute because you know that the first A0 term is when n is 0. So 0 squared plus 1 is 1. And then 1 squared plus 1 is 1. There is no half squared because set of natural numbers counts only integers. 0, 1, 2, 3, 4. So there's no half. There's no 3/4. There's no 1.17. It's just whole numbers. So 0 squared plus 1 is 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5. And you keep computing, and then you can calculate however many terms you want in that sequence. Another example, you can call it also Bn, right? Next example could be 2 to the n minus 4, right? 2 to the n minus 4. If you start at 0, 2 to the 0 is 1, minus 4 is negative 3. 2 to the 1 is 2, minus 4 is negative 2. 2 squared is 4 minus 4 is 0. 2 cubed is 8 minus 4 is 4. 2 to the 4 is 16 minus 4 is 12. And you can go as long as you want. So that is another example where the first one looked more like resembling polynomial. The second one is clearly resembling exponential. You can have anything, as long as it has this n. Here's the really cool one. Let's say Cn is equal to cosine of n pi. So how much is cosine of 0?
1.
Great. How much is cosine of pi?
5.
-1. And how much is cosine of 2 pi? And then 3 pi? And then pi? You see this? It's awesome, right? You can get that. So sequences are really cool. I don't know, maybe you have different definition of cool. This is my definition of cool. Deal with that. So you see examples of some sequences. You have the formula, and you get to generate sequence. Let's do one more. You generate this one on your own, and then tell me what it is. Give me first 4 terms. First 4. What's up? You have it? Check with people. All right, so what do you have? So 1, 2/3, 1/3, 4/27. I'm thinking you're speaking because I can see your mouth moving. But for the air conditioning, I'm not receiving any sound waves, because there is a destructive interference between the 2 waves, the waves that you are producing and the wave that the air conditioning is producing, and they're canceling each other out. So if you intensify your sound waves, I will definitely hear it.
Well, for computer science, there's a, well, first off, they already put this in but also, well, not just a full, but also, there's a limit to how many decimal points they would be able to have.
Yeah, that depends on what kind of number you have, 60-bit, 64-bit number, 120, yeah. So that depends on how much it can store. But computers start making algebraic mistakes up to the point where they can't understand the number at some point when the number is sufficiently large. So if you have 64 bits, that's in binary 263 plus 1, right? So whatever the calculation works out to be after that number, computers understand only multiples of 2. They don't understand odd numbers anymore. So it rounds. But we're not concerned with that because over here we have infinite precision. So there's one thing of what we can actually pull off in engineering or computer science, and mathematics reality is that we actually have the exact.
So this would be an infinite.
Yeah, it will be an infinite. Each one of these is infinite. All right, great. So let's see. So we've seen now that we can generate the sequence using the formula. Now we can also generate the sequence using something that is called recurrence relation, which is the formula which generates the sequence based on the previous input. So recurrence relation is some kind of a function which includes a n and then maybe a n minus 1, a n minus 2, and so on. To give you an example of this, say that your a n is equal to 2an minus 1 plus 3. And we define a0 as, let's say, 4. You have to have a starting point, because if look at the screen, the new value depends on the old one. One more time, look at the screen. New value depends on the old value. So you have to have a starting point, which is the old value for the first time, and then you keep generating, so then the cycle starts. So looking at this, clearly egg first, right, and then the chicken. So what's a1? a1 is definitely 2a0 plus 3, which is 2 times 4 plus 3 equal to 11. a2 is 2a1 plus 3, which is clearly 2 times 11 plus 3, which is 25. a3 is 2a2, you always take the previous one, plus 3, which is 2 times 25 plus 3, which is 53. a4, and I'm going to stop here because I'm getting bored, 2 times 53 plus 3 is 109. So I'll put 3 dots because your sequence is starting with 4, that's given to you, and then you have 11, 25, 53, 109, dot, 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 going forever. Recurrence relations can use more than one input. So you might be familiar with Fibonacci sequence. Fibonacci sequence is the sequence that has a recursion with 2 terms, the first 2 inputs. So a2 is a0 plus, an is equal to an minus 1 plus an minus 2. So these are, right, if an is the current one, then n minus 1 is the previous, and n minus 2 is the one prior to that one. So if I write this and I say that A0 is 1 and A1 is 1, we are starting Fibonacci sequence by writing the first two terms, and then the next term is the sum of the first two, and then the next is the sum of the last two, and the next is the sum of the last two, and you keep doing that until you get bored. So Fibonacci sequence is using the recursion. Sense the tone of the title. Test for convergence of sequences. Are we clear on the tone of the title over here? Sequence can converge or diverge. Converge means that in the limit, as you take infinitely many numbers, it will converge toward a certain value, or diverge, go to positive or negative infinity. So the test is like this. You take the limit as n goes to infinity of your an. That can have two separate answers. L, which we say converges to L, or positive and negative infinity, where we claim divergence. This is your test for convergence of sequences. This is the first test that you will be memorizing out of 11 tests in chapter 10. You remember that you memorized the formula for disk method, shell method, washer method, length of the curve, surface revolution, right? You memorized those formulas and then you use them. In chapter 8, you will be memorizing these tests. Each test will have its name and the way how it's done. And you either memorize and use the test, or you just stare at the problem and that's it. You can't come up with stuff in chapter 8, and you will see that intuition will most likely be wrong many times. Intuition will be wrong, and the gut feeling would be wrong. So memorizing these tests and using them when it's appropriate is the key to success in what's labeled as the hell chapter in Calc 2. So anytime when I do something like this, that is your test. And as I said, you're going to have 11 of those. You are going to have one test for sequences, which is this one, and you will have 10 for series that we will start covering tomorrow after the exam. So you will be memorizing these guys, and you will see that this chapter is either going to be extremely easy or just hell on earth. It's one or the other. There is no, it's okay. That just doesn't exist. So now what I want to do is I want to test some of the sequences. So test for convergence. An is equal to what I had earlier, n squared plus 1. Would this converge or diverge? Diverge, right? Because you are immediately going to hit it with the limit. and you're getting infinity, just put D in a circle, means divergent, and you move along with your life. That's all it is. That's very quick. By the way, every single problem that we are going to do in this chapter is a limit problem, which means chapter 2, right? Limits, and make sure you know those Lhopitals Rule derivative limits, right? Where you use derivatives, so you can operate. Next one. Test for convergence. AN equals to 5 over 2 to the n. Very good.
Am I right? Because if you put down like a negative, then you can't put like a negative number.
What do you mean?
If you put down like 5 divided by 2 to the
What?
negative second power.
Well, you see that n goes to infinity, right?
Yes.
So denominator is what?
Goes to infinity.
So 5 divided by infinity is
Is down there.
0. So converges to 0. And we're done. Test for convergence. AN is equal to 3n squared minus 1 divided by n squared plus 1. Nice.
Convergent.
What?
Convergent.
Keep talking.
It's 0. Like you plug in infinity squared plus by 1, it'll cancel out, it goes to 0.
What cancel out to go to 0?
It's like 3,
How do we do this limit from Calc 1?
3 infinity square.
Ratio of leading coefficients to the powers of equal.
Ratio of coefficients, yes. So we divide by n squared everywhere. That's the highest exponent. And then we have limit n goes to infinity of 3 minus 1 over n squared over 1 plus 1 over n squared. Now 1 over infinity goes to 0. 1 over infinity goes to 0. 3 divided by 1 is 3 converges to 3. Nice. Next one. Test for convergence. AN equals to 1 plus 1 over n to 3n.
Remember doing this one with Professor Armstrong.
All right. Bake on this one a little bit. What? Where's the answer? What do we have? What happened? It's convergent, but it's not to 1.
I remember doing parentheses 1 plus like 1 over n to 1/3 parentheses 3n.
Nope.
You probably had to remember this when you were back. You had pieces back in Calculus 1, but when you do like 3n or like the 1/3, you find
Nope.
Is it convergent to 20.0855? That's what I got.
You said no to 1.
Most capitals. Yeah.
Let's go then with 1, all right? Because that answer is less psychotic. The hell you found that?
I plugged in 1 million and 10 million. They go
So you got the approximation. Yeah, you know what it is. E cubed.
What is it?
E cubed. Because the limit n goes to infinity of 1 plus 1 over n to the n, and then you have everything cubed, is just definition for e, and then you have a cube.
That's what I was talking about earlier.
You didn't say e.
No, I meant like basically you have to separate them out, dimensioning 1/3, and then you said like 3n.
Oh no! If you're doing this, you actually have to use the Lhopitals Rule, logarithmic limits, or whatever you want to call it. So to do this, you would have to go with ln both sides, and that allows you to drop down 3n. I don't want to spend 3 hours to write all of this out, but you can find this when I teach the Lhopitals Rule. Look at the Calc1 from on YouTube. You will see. So guys, there is now you have to apply the limit. Oh, I forgot the limit. Oops.
-1.
And goes to infinity, and you see that this is infinity times 0. So you use 1 over f trick. You learned in Calc 1 all of this. So ln y is the limit, and goes to infinity, and then you have your ln of 1 plus 1 over n divided by 1 over 3n. And then as you do this, eventually you will get that ln y is equal to 3, e both sides, and you get your y is equal to e cubed. There's about half a page work where the 3 dots are. So you have to take independent derivatives, top and the bottom, and then we'll go. So what was your answer?
It was right. I said 20.08.
And how'd you get that?
Well, I plugged in to the original one. I plugged in 1 plus 1 over 1 million. And then I plugged in.
Yeah, the heck. Yes, okay. All right, sounds good. Yeah. Those SAT skills, right? One day I'm gonna sit and learn those, you know. Say, can you tutor me SAT? No, I can't. So how you can beat the system using calculator? Like, I'm incapable. I'm sorry. So we're skipping all of the series talk because all of the series talk will be dealt later. All right. So now for sequences, we also have graphing, right? Now, when you're talking about graphing sequences, remember that 1.2 doesn't exist and 1/2 doesn't exist and e doesn't exist as input. So what we get are series of discrete dots on the graph. So if I want to graph y equals x, we get to graph a 45-degree line through the origin and it's a continuous line that hits every value of x and gives us a lot of values on y. Comparison to that, an equals n would be the same thing, except now we are only looking at the first quadrant. These are your input n, and this is your output an. You get a dot at the origin, dot at 1, 1, dot at 2, 2, 3, 3, 4, 4, 5, 5. You see that there is correspondence between the two, right? But you don't have a value for 1.7 or 3/4 or 17/2. Those values don't exist. Only exist for 1 and 2. So the input are only these whole numbers, because remember that our sequence is ordered through this set. Next example for the graph. Let's use y equals, say, 2 to the x. You know that that's exponential graph. It goes through 1, and then 2, and then 4, and then 8. An equals 2 to the n is going to have only dots on the positive quadrant. So I draw the dot for n equals 0, n equals 1, n equals 2, n equals 3, and then it becomes too large, right, to draw. So the input axis is n, set of natural counting numbers, and the output axis is an, which are the answers, the good old y. So we can graph these. Every time when you overlay the two graphs, they have to follow exactly. So that's graphing. Now, the question is, what does it mean, convergent, divergent, and so on, right? If you look at these things, you might consider an of 1 over 2 to the n. How does that look like as a sequence? Well, at 0, we get 1. At 1, we get a half, and then a quarter, and then 1/8, 1/16. So it keeps doubling, and the denominator, the numbers are becoming smaller. So if I graph this, I'm going to use on an 4 squares for number 1, and over here I'm going to use each square. No, actually 2 squares could be, right? Yeah. The first rule of engineering is draw big. Don't remember anything, remember that. First value is at 0, which gives us 1. At 1, we have a half. This is where a half is. And then a quarter, and then 8, 16th, 32nd. And you see that the tendency is, as n goes to infinity, that an will go to 0. So that's what it means to converge to 0. As you're walking to the right, the y value settles at that number. So technically it's the horizontal asymptote, right? So if you know this, then you can easily answer because you're prepping for a test, I hope. If I ask you an of inverse tangent of n, what happens there?
Well, I was going to ask you a question.
Okay, what's the question?
Well, it's kind of a theoretical question. It's basically whether it's kind of convergent or whether it's not basically the scale that you're looking at it. So if you're looking at it like on a scale of 1, it's obviously zero. But if you're looking at it really massive scale, it's like zero. But if you zoom in really close, even when n is like really close, zoom in close enough, you'll still see the difference.
But the convergent is not looking at one location. It is the trend of the entire thing. So every time when you say, see, limit as n goes to infinity. So you have to have that motion, goes to infinity. So it's not stationary. Vertical asymptote is stationary at x equals 2 or something. But the horizontal asymptotes, which is what we're dealing here with, the n is going to infinity. So there's that motion that, yay, right? Like that, always moving. And as n is trying to be infinite, what's happening with all the y values? Because limit in a nutshell is figuring out y values. Yeah, they're getting to 0. Now, what's the next question? What happened? Yes, so if I'm to test this, n goes to infinity, what do we get? Pi over 2, exactly. We beat this one to death. The next order of business is to learn vocabulary and some of the rules, and we're done. Limit laws for sequences. So assume that the limit n goes to infinity of an is a, so converges to a, and limit of bn is b, converges to b. Number 1, limit of an plus minus bn is going to be a plus b, or minus b, depending on which one you have. Constant multiple so this is technically the rule that says you can kick constants outside. There is no product rule for this, so it just goes straight through because limits are like that. And the quotient rule, no quotient rule. Just go straight through, make sure the denominator is not 0. Now, clearly, if you review limits from your Calculus 1 class, you will not have many issues and troubles in your in this section. Terminology. Is non-increasing the same as decreasing?
Yeah, no, they're different.
They're different. They're different. So we have to, all of these definitions are given on page 608. So terminology for sequences. So sequence AN is increasing if AN plus 1 is bigger than AN. This just tells you that the next term is strictly bigger. And then you have non-decreasing. So AN is non-decreasing. If AN plus 1 is bigger or equal than AN. So you are allowed to have the same numbers. So Fibonacci sequence goes 1, 1, 2, 3, 5, 8, 11, right? Let's go 1, 1. Just because you had that 1, 1 once, right? You can't call it increasing. It's non-decreasing. That's what it is. Because there is at least one instance where two values are the same. So Fibonacci sequence is called non-decreasing because you have 1 and then repeated 1, right? So from 1 to 1 there's no increase. There is increase everywhere else, but for the first two terms there is no increase, so we can't call it increasing. We have to call it non-decreasing. So you have three things: decreasing, constant, and increasing, right? So if you want to keep increasing and constant in one, it's easier to say non-decreasing than to say could be constant or increasing. It's less words used, so that's why. Then we have AN is decreasing. If AN plus 1 is strictly less than AN, so the new term is smaller than the previous term. And we have non-increasing now. Then AN. AN is monotonic. If it is either non-increasing or non-decreasing. And the last one, AN is bounded. If there is a number call it capital M, such that the entire sequence AN in absolute values, because you want to grab all the points, is less than M. Yeah, it's a bound. Less than, right? Because it's a bound, so sequence has to be less. This needs to be bigger because it's a bound. You can't go over the bound. Well, that's why they put the absolute values, right? So if you break this compound into inequality, then you have to introduce positive and negative, and then it would switch. So technically what this means is that AN is trapped between a negative M and M, but mathematically compressed. That's the way you write it. Another theorem. A bounded monotonic sequence converges. Which makes sense. If it's bounded, it's always converging to that bound, right? If it's monotonic, it has to follow the bound. So the bound would be the limit, and the part that it's monotonic makes sure that it goes to that limit. There are two graphs that are associated with this, which are pretty good. So here is your bound M. And you have non-decreasing. And here's your bound M. And you have non-increasing. So clearly both of them converge. The last concept that we are covering, and then we're going to take the break and then review, is your lifesaver for some of the limits. All of these limits are going to infinity, and this part over here is growth rate of sequences. We did something similar in Calculus 1, growth rate of functions, to take certain limits faster. So now the growth rate of sequences goes that any sequence that it's ln to whatever power of n grows slower than the polynomial looking one, which grows slower than the multiplication of the two, which grows slower than when you multiply two polynomials, which grows slower than the exponential, and they don't have it here, which grows slower than the factorial. That's what I tossed in. That grows slower than n to the n. We can quickly show this by observing numbers. N, 2n, n squared, 2 to the n, n factorial, n to the n. 0, 1, 2, 3, 4, 5. So 2n doubles each one of these and clearly grows faster. Because by the time you are at n equals to 5, the other one is at 10. So it grows faster. But then n squared grows even faster. Look how in the beginning it's kind of equal and then loses and then it's equal. But then when it catches up, it takes off. 2 to the n goes, okay, 2 to the 0 is 1, 2 to the 1 is 2. So it kind of starts winning. And then as you can see on the line number 5, it wins. So it was, you know, struggling in the beginning, and then it took off. Factorial one grows much faster. If you look at this, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, because 2 times 1, 3 factorial is 3 times 2 times 1, which is 6. It's losing, right? But then the next one is times 4, which is 24. The next one is times 5, 120. So when this one takes off, right, it really goes. No. 0 factorial is defined as 1. There's no calculation for it. There's a proof, but there's no calculation for it.
If it's 1 times 1, it would be 1, but if it's 1 times 2, it would be like 2.
It doesn't follow the pattern.
Okay.
The pattern is only for 1, 2, 3, 4, 5, and so on. 0 factorial is defined as 1. And I can show you some stuff later. Now n to the n, 1 to the 0 to the 0, right? 1 to the 1, and then 2 squared, 3 cubed, 4 to the 4. Look at that one. And then 5 to the 5. That's 3025, I believe. 3125. That's what I said. Please pay attention. Look at n to the n. Now, why is this good to know? Because when you are hit with the limit goes to infinity, if you know growth rates of functions, you can immediately claim the answer. Slow divided by fast, or slower divided by faster, is 0. Faster divided by slower is going to be infinity. And if they are of the same growth rate, then you have to do the math. So, if you have limit of 2n divided by n to the n, that's immediately 0. Because the function on the bottom grows, the sequence on the bottom grows much faster than the one on the top. And you eventually end up dividing a number with infinity, and you get 0. Yes, faster or slower goes to infinity. And slower over faster goes to 0. So we have a situation here, slower over faster goes to 0. Another example would be limit n goes to infinity of, let's say, 3 to the n over n to 1 million. What is that? It's infinity. Because the numerator grows much faster. Yeah, I know I have a million on the bottom, but it will catch up. This is exponential. This is polynomial. Polynomials always grow slower than exponential. So it doesn't matter that it's a million. It could be 100 million. It could be whatever you can put there. The numerator will grow faster because it's exponential. It's the type of the function, not which numbers are involved. So these are some of the introductory points. You have to remember that sequence is the ordered list of numbers. Ordering is done with n, which is counting set, 1, 2, 3, 4, 5, and so on. You have the formulas, you have recursions, you have all the words. Graphs are pretty much the same, except you don't have the line, you have the dots. And then the most important part is the test for convergence of sequences. And that is that when you see a formula, you take the limit n goes to infinity, and that will either be a finite number, in which case converges to that number, or it's going to be infinity, where we claim it diverges.
But just to recap what he said, is that basically all he says how progress upon what we get to the infinity is 0. Like where he said 10 for conversion,
Yes, so test is the limit test.
Yes. And then the graphing.
Yeah. And limit test is the only test that you have for sequences. We are going to have 10 different tests for series later on. So tomorrow after the exam, I'm going to define a series as a sum of the sequence. We are going to remove commas and put pluses. And then that can converge or diverge depending on what kind of terms you have. And we are going to spend entire chapter talking about those, and then later on upgrade them into functions and upgrade them into periodic functions in Fourier analysis if you continue taking math and so on. So that's it for today. We are going to take a break and then review.